to compare the why do I call this particular hormone a glucocorticoid? I have already told you, because it has a certain action on the liver, which on the liver it can mobilize it can mobilize the carbohydrate from the cell, and it can release glucose. And one of the most the hormone that has a very strong glucocorticoid activity we have already seen is cortisol. But does it also have a mineralocorticoid activity? And what do I mean when I ask a question, what do I mean by the cell having a mineralocorticoid activity? Basic question. I have defined you what is glucocorticoid activity, that it can mobilize glucose from a liver cell. What is a mineralocorticoid activity? Mineralocorticoid activity is simply the capability of the hormone to act on the kidney and to make sure that the sodium does not go away. I want to retain the sodium. Principal cell, hello. Hello, are you with me? Principal cell, the late distal tubule, okay? Intercalated cell and the distal cell. Now I am talking of what? When I talk about aldosterone, I am going to talk about principal cell, about which you have already spoken 100 times. Principal cell. Okay, so far, good. Now, does cortisol also have mineralocorticoid activity? That is where biology starts getting fuzzy. It does. It has predominantly what? Glucocorticoid, but it has some. Aldosterone, does aldosterone? Well, it is a very, very powerful mineralocorticoid hormone, and I am going to study it because it just acts on the principal cells and brings about the reabsorption of sodium ions. Does it have any glucocorticoid? Well, it has a little glucocorticoid activity. But then question comes as to how are you going to standardize, okay. Therefore, to standardize, there is a method. We say that let us talk about cortisol, average plasma concentration is about 12 whatever it is micrograms per 100 ml of blood, average secreted about so much, and whatever is glucocorticoid activity is 1 and mineralocorticoid activity is 1. Is it just a standard I am using? Whatever activity, so I will give cortisol, find out how much of glucose is being released, I will call it as activity 1. I will give cortisol on the kidney, find how much of sodium it absorbs, I will call it as 1. That is my standard, okay, so far. And then I am going to compare it with others, and what I find is, whereas the cortisol is, cortisol, let us say glucocorticoid activity is 1, cortisone is 0.3, aldosterone is 0.2. Are you getting the standard? Means, does aldosterone have glucocorticoid activity? Yes. How much it is? It is 1/5 that of, hello, are you with me? I am not talking Greek and Latin, okay. It's very simple. We are just comparing the activities of different molecules. But what is amazing is, let us talk about the aldosterone. What is striking here? The mineralocorticoid activity of aldosterone is how much? Times that of what? That of cortisol. Huge amount of, okay, therefore we say that it is a very powerful, okay. Then this slide is very interesting for yet another reason. See, this is actually a very old story, almost 1950 onwards. The organic chemistry people have done miracles. They have literally synthesized thousands and thousands of molecules with a steroid, put OH there, put this, they put that, n number of molecules they have. And what do you call them? We call them, and then do what? And then look for its biological activity, okay. And some of the molecules have emerged such a powerful molecule that one of them is called as what? Dexamethasone. The chances are that if you go to a pharmacy and buy an anti-inflammatory agent or a topically applying cream which is anti-inflammatory, most probably it will contain dexamethasone. Is it a naturally occurring steroid? Yes or no? It is not a naturally occurring steroid, okay. But then you will find that it's much more powerful than the naturally occurring steroids. Okay. So we have a large number of prednisolone, methylprednisolone, dexamethasone, 9-alpha fluorocortisol, n number of, only some of them which are in clinical practice have been here, but you can't really learn about steroids without knowing their profound impact on the pharmaceutical industry. Have I conveyed my point? See, they are widely, people, the chemistry people have done miracles here in coming up with little variation here and there, and okay. It goes in the blood by like thyroid hormone. This also, there's a large protein molecule, okay, large protein molecule, and we call it as, what do we call it as? Corticosteroid binding globulin. Are you immediately reminded of that? That what? In the case of thyroid, we had a large protein molecule. That protein molecule would bind to the, and it would have the same function. What do I mean by same function? What do I mean by that? Stabilizing. Okay. Don't try to increase the biological half life of the molecule. Okay. And so here we have the, so here we are talking about a very large molecule. It's a protein molecule. It has molecular weight of about, how much is there? For, can you read for me? Molecular weight about how much? 58,000 is the molecular weight of the large protein molecule, okay, and then it can keep, and this molecule, and there are several of them, not one of them, there are several of them, and all of them are put together, and they are also called as transcortins. They are called as what? Corticosteroid binding globulin, or they are also called as transcortins. They are huge proteins. They are all synthesized by the liver, and they serve to bind, and these proteins have far more affinity for cortisol. They also have affinity for aldosterone, but the affinity for aldosterone is much less. Look, what are we talking about? These proteins, different proteins are there. Where are they? In the blood. Where are they coming from? They are coming from the liver. What do? They bind to these steroid hormones. Good. And cortisol has a larger, therefore, because cortisol binds more tightly to that protein, okay, therefore it can be degraded, it is degraded much more slowly. Are you okay so far? And therefore its biological, what is the biological half life of cortisol? For, please read for me there, is how much? 1.5 hours to 2 hours, okay. And aldosterone has, which binds loosely with less affinity to the transcortin molecule, therefore it has a shorter biological half life, about how much? So, please tell me the biological half life of cortisol, fill in the blank, and that of the aldosterone, fill in the blank.
Greater.
Greater. Cortisol is how much?
1.5 to 2.
And aldosterone is how much? 15 minutes. How much it is? It's 15 minutes. Okay. These molecules are again degraded. How are they degraded? Very interesting. We know this molecule. Very familiar, this cortisol molecule, okay, so far. As it is passing through the liver, okay, the liver has enzymes. Those enzymes will add this particular moiety to the, can somebody tell me what is this position? 3 position. At 3 position, it adds another molecule which is called as, it's called as conjugation with a glucuronic acid. This is called as glucuronic acid. The moment glucuronic moiety is added to the position 3rd of the molecule, either glucuronic or sulfate, one of the two. Two things happen. The molecule becomes more soluble, most important, and secondly, this molecule now cannot combine with its receptor. What have you really done? Yeah, you have completely inactivated the molecule. Okay, and because it is more soluble now, please remember, steroids solubility is very, very low. Are they insoluble? No, they are extremely, solubility is very low. But when you add this, it becomes more soluble, therefore it can be readily filtered at the level, it can be readily filtered at the level of the kidney, it can be thrown out of the body. Now, this has a very interesting implication, I will tell you how. We vertebrates do not have an enzyme to break the steroid nucleus. This will remain as that and it will get out of your body as the steroid nucleus. Are you with me so far? Okay. Yes or no? So, whereas some of it goes by way of urine, some of it actually also goes by way of feces, by way of bile. Okay. What is the application of this observation? Scat analysis the analysis of the stools of the tiger and the panther and the wild animals, okay, to find out about their endocrine system. Okay, you can just collect the samples of the droppings of those animals, okay, because they still have these steroid nucleus. Okay, and from that, from the chemistry of this, you can work out as to whether what is the sexual status of that female, or what you can work a lot. There is huge amount of branch of endocrinology there, where you can do the scat analysis and find out the physiology of the animal without even drawing a drop of blood. Hello, are you with me? Are you getting the argument? You see, you can't go and draw the blood of a tiger. Okay, okay, you can't do that. Okay, so collecting these samples, okay, fecal samples and the urine samples, if you can do the analysis and you can find out about. I want you to remember, because recognizable hormonal products can be identified in the urine, it is possible to estimate the daily secretory rate of steroid hormones by non-invasive technique of analyzing urinary excretory. Okay. Now let's talk about the importance of aldosterone. I told you once, I will tell you once again. Just open a mouse or a rat, remove both the adrenal glands, suture up the animal, and the animal generally will die in about 6 to 7 days. Okay? What did I say? It will die, absolutely sure. But you see, this is the animal is in the cage, and in the cage you provide a bottle, so that the animal can drink water. Through that water, if you just give saline, the guy survives. Are you getting the argument? There is a cage in the animal house, there is a cage, the water bottle, and the animal comes and licks routinely, and you just have what? We can just give one tap water will do for the animal. Okay? If you just give tap water, the animal will die. But then what you do is you remove the adrenal cortex, both, okay, it will die. But if you in the bottle, if you provide what? Salt solution, slightly concentrated, maybe 1 spoon, 1 or 2 spoons in that bottle, the guy lives. Why?
Because the cortex,
because you are right.
mineralocorticoids are not there.
So what is happening?
So sodium is being lost.
How?
Absorption.
It is being lost. It is being lost. How? It is going. It is getting lost. How? Through urine. I mean, come on. It is getting lost. How? Through urine. So and what are you really doing? Supplementing. The right word is supplementing. You are just supplementing. Okay. As long as the animal is not normal. Okay. Animal is still very sick, but it doesn't die. Okay. This simple experiment, okay, proves the profound importance of aldosterone. Okay. Aldosterone. You give aldosterone, it is able to say, okay. So let's see now why aldosterone or not having aldosterone kills. Okay. So this is what I am showing. I am just showing you cells, and there is a blood vessel, there is intracellular fluid, there is extracellular fluid. Are you okay so far? Done. So now you have removed both the adrenal glands, and as a result of that, the animal has started losing sodium ions through the urine. Actually, you know something, if you start collecting the urine of the animal whose adrenals have been removed, a huge amount of sodium. I mean, all you have to do is to the sham operated. What do I mean by sham operated? What is sham operated? Sham operated means it's a control animal. In the control animal, the poor guy, again you give a cut, okay, on the back, okay, and do everything, but don't remove the adrenal glands. And now what is this? This is a sham operated. Sham is false. Is a real surgery or false surgery? False surgery. And why do you do that? Because you want to make sure that you are comparing the experimental animal in which the adrenals have been really removed with an animal which, not with just a normal, no, with the animal which has been sham treated. Means what? Which has been subjected to surgery. You have to anesthetize the animal, you have to open the animal, you have to suture the animal, you have to do everything, but don't remove the adrenals. What will I call that animal as? Sham surgery. And I am going to do what? I am going to compare the urine of the sham surgery animal, where I find that urine is almost normal in terms of sodium ion content, and then I collect the urine from the other fellows whose adrenal glands have been corticus have been really removed, and what do I find? There is enormous increase in the amount of sodium ions in the urine. Is that point taken? Now, as a result of I already know that in the blood and in the extracellular fluid, the sodium ion concentration is about 140 milliequivalents per liter. Hello, sodium ion concentration 140, about something like that. Okay. Now, as a result of the surgery, okay, and as a result now the guy has started losing lot of sodium in its urine, it has fallen to about 120. How much? 120. So, the sodium ion concentration here is fallen. As a result of that, osmolality has fallen. Okay. Now, the osmolality of the cells is still normal. Okay. As a result of that, the cells will start drawing water from the extracellular fluid. Outside is dilute, they will draw water. Are you with me? As a result of that, there is a lot of water transfer from the extracellular medium into the cell. As a result of that, the extracellular volume, which has to be homeostatically standard, okay, that is reduced. And then the animal knows from what you call as, read here, hypovolemia. Hypovolemia means the total amount of fluids that we have, certain amount intracellular, certain amount of extracellular. As a result of surgery, the extracellular volume has started reducing. As a result of that, actually death is because that greatly contributes to the, whereas the aldosterone is necessary for maintaining sodium ion concentration. It also it does exactly opposite with reference to potassium ions. Means what? Extracellular potassium ion concentration is extremely low, about 4 milliequivalents per liter. Extracellular potassium is very low, we have done that 100 times. Okay. Now, when you remove the adrenal glands, then that potassium goes up. Potassium goes up how much? How much? Potassium goes up from where to where? From where to where? Where to where? 4 to 10, 4 to 8, almost double. Are you okay so far? Now, that is a very serious condition because, you remember, forget about everything else, let us focus on the heart. Okay. First the sodium ion channels open, okay, as a result of that depolarization, and then the position, and then of course the calcium, the plateau, but then it goes down, because the potassium ions go out. Are you with me? Potassium ions go out, and therefore the curve goes down. Now, the potassium ions go down because there is a gradient. There is huge potassium inside and there is very low potassium outside. There is a gradient. With that gradient, the potassium ions go. Are you with? Okay, so far potassium ions go because there is a gradient, and that gradient is because potassium is about 4 milliequivalents per liter. If that 4 becomes 8, what happens to the gradient? Gradient is greatly reduced. When the gradient is reduced, the potassium ions do not go that far. When they do not go that far, they accumulate, some of them accumulate on the inside. When they accumulate on the inside, they partially depolarize, okay, which is not a great idea. As a result of that, the whole heart, functioning of the heart becomes very weak. Okay. Now, let us talk about the, so I am sure you understand this figure. We are talking about what? We are talking about the principal cells in the distal, this is the distal convoluted tubule. We talked about the intercalated cells, and we talked about the, we have done this image. I am showing it to you for the maybe third or fourth time. So, what have we done? We have taken one cell from there, and we know what that cell is. What is that cell? It is a principal cell. And what does okay. And on the basal side, what are you going to have? A pump. And on the apical side, what are you going to have? ENaC. What is the full form of ENaC?
Epithelial sodium channel.
Very good. Epithelial sodium channel. Now, the proteins which make up this channel, and the proteins which make the sodium potassium, and also the proteins which make up yet other, look. There are about 100 different kinds of potassium ion channels available in the animal and plant world. 100. To my knowledge, there may be more. Okay. Now, here author talks about one MAC-K, ROMK, whatever. All these, listen to this. Aldosterone has action, has genomic action which keeps on activating large number of genes, and those genes, they have their mRNA, they have their proteins, and some of the proteins I am talking of are here and they are here. Are you getting the entire story now? So, it is because those proteins are there in the principal cells and they are functioning because in the principal cell there is a receptor for aldosterone which takes aldosterone, that receptor goes, how that mechanism of action I will take you. It has a genomic action and you have all those proteins. So, huge number of, there is under the influence of aldosterone, you have huge number of the copies of this protein system, you have this protein system, and as a result of the pump you can imagine there is very low sodium ion concentration. Done? Hello? Yes or no? And then as a result of this channel here, because there is low sodium, the sodium will be absorbed from the lumen. Okay. So, whatever sodium that has been absorbed, huge amount of will be absorbed here. Are you okay? Is everybody okay with the story? Okay. So, remember, epithelial sodium channel proteins are aldosterone increases sodium potassium pump and facilitates the insertion of epithelial. Okay. Oh, this is. Can somebody please tell me what the author is trying to tell us? Insertion of epithelial sodium channel proteins. Why is the word author? Why is the author using the word insertion? Vesicles. There are vesicles. We have done this. Yeah, arginine, vasopressin. There are vesicles. Okay, those vesicles will have those proteins, ENaC proteins, and they are inside, so they are pretty useless. Under the influence of aldosterone, they will insert on the apical membrane. Hello, and once in the apical membrane, they will facilitate the influx of sodium ions from the tubular lumen into the cells. We have done this again, where the author is telling us about the structure of the proteins of the ENaC, and let us try to understand very briefly what is the mechanism of action of the aldosterone on the target cell. The moment I use the word target cell, what am I talking about? Principal cell. What am I talking about? Principal cell. Okay. What about the principal cell? Okay. So, here is the aldosterone molecule. Okay. Where does it come from? It comes from the blood. Is it possible that yes, it is bound to the large protein molecule? Yeah. It is possible that it has been roughly found that about 60% of the aldosterone in the blood is bound, whereas 40% is free. So, some of the free molecule can come out of the capillary, no problem. Then it can, it is a steroid molecule, okay, okay. Then one other thing I have to very clearly mention. The steroid molecules have one advantage. What is it? Because they are lipid soluble, they can go anywhere. So, you do not need a receptor in the plasma membrane. Are you okay? You do not need it. So, where is the receptor located? The receptor is located in the cytoplasm. Okay, and the author is calling that receptor is MR. Why is author calling that my aldosterone receptor as MR? Mineralocorticoid. It is a mineralocorticoid receptor. Okay, so far. Now this, and this mineralocorticoid receptor is normally under resting conditions, it is attached to another chaperone protein, okay, which is here, and when the aldosterone comes, that chaperone protein is removed. Are you with me? And then aldosterone will combine, which is a very small molecule, it combines with a huge molecule, which is the receptor for or mineralocorticoid receptor. That receptor is about 600-700 amino acid, huge molecule. So, receptor is a big molecule, aldosterone is very small molecule, but as a result of the receptor combining with the aldosterone, then it enters into the nucleus, it combines with its promoter or whatever, and then you have a range number of proteins coming in. They include the pump, and they include what, and they include a huge number of things are happening as a result of, okay, and let us focus on these two mainly, the pump and ENaC. Are you very clear now? What have we discussed as to how does aldosterone bring about the insertion of the. Now, this is very, just focus on this, a very interesting phenomena that is operating now. Listen to this. There is a problem. Let us appreciate the problem first. So, you really enjoy the solution. The MR that we have seen in the previous slide, MR, what is MR? It has affinity for aldosterone. Good. There is a problem. The problem is that receptor also has affinity for cortisol. Hey, there is a problem. There is a problem. Because the problem is because the amount of cortisol in the blood may be 50 or 100 times more than that of aldosterone. Hey, come on, wake up. There is a problem. What is the problem? There is so much of cortisol there, and that cortisol has affinity for the same receptor. So it's without fail that cortisol will dominate, and the poor aldosterone will not have any. I mean, then you will have all the effects of you will have. If downstream you will have, instead of having whatever control of aldosterone you have 100 times more effect. You understand the problem? Very serious problem. First appreciate the problem. So much cortisol. I mean, the nature would have done a wise thing in coming up with the mineralocorticoid receptor that does not have affinity for cortisol. That would have been great, but it has. Now let us see how the nature has come up with the solution. The nature has come up with the solution is that cortisol, as it enters into the cell, it is acted upon by another enzyme called as 11 beta hydroxysteroid dehydrogenase. Hydroxysteroid dehydrogenase, there are 1 and 2. And this converts the cortisol into another steroid hormone which is called as cortisone. And that cortisone has no affinity for the receptor. Are you with me? Are you with me? So the cell has, the biology has created a problem and biology has solved the problem. How it has solved the problem? By not allowing the cortisol to come in contact with the receptor. How to do that? Well, we are converted into what? Cortisone. And does cortisone have affinity for the same mineralocorticoid receptor? No. And as a result of that, the mineralocorticoid, so the aldosterone here, and then you get the rest of the changes. Are you okay so far? Good. Now listen to this. I am going to use a Hindi word. Let me see how many of you know the word. How many have heard the word Jeshtamad? Raise your hands. How would you describe it in other language? I know the English word licorice, but that does not mean anything. We use it in the kitchen, you know, it is, how do you describe? It's a piece of bark of a wood. You can eat it raw, it's also slightly sweetish. Does it make sense? What do you call it as in English? In English you call it as licorice. What do you call it as? Licorice. So I have written here somewhere. Okay. It is called as licorice, root of the plant Glycyrrhiza glabra, also known as what? Another problem, this if you take too much of it, it combines, it blocks the enzyme. What enzyme? 11 beta hydroxysteroid dehydrogenase. Therefore, the cortisol cannot be converted into cortisone. Therefore, cortisol binds with the receptor for aldosterone. Okay, and then you have excessive effect of aldosterone. Is it the effect of aldosterone? No, it is the effect of cortisol, but it is acting like aldosterone. Downstream, oh look, you see there is a receptor. Where is it? It is in the principal cell. If it excites, what it will do? It will go and keep on absorbing sodium. Now you can activate that receptor either by aldosterone or by cortisol. Under natural conditions, cortisol is not available because it is converted by the enzyme into what? Cortisone. But if you have eaten too much of licorice and if you have inhibited that enzyme, then cortisol is available as a cortisol. It will combine with, and then you will have all the downstream effects which are like aldosterone, which means there is too much of aldosterone, which means you will start absorbing a lot of sodium, and you will have symptoms of what you called as hyperaldosteronism. What did I say? Hyperaldosteronism. You will access of, okay, an amazing phenomenon. Okay. Whereas the primary site for the action of aldosterone is what? I said just now, we have been hammering it 100 times, principal cells. Well, there are two more places, sites where it can also act, several places actually, including alimentary canal, but some of them clearly are in the salivary glands. You remember salivary glands, the saliva is secreted and saliva has a lot of sodium ions in it, primary saliva. Then by the time it passes through the ducts, okay, a lot of sodium is absorbed. That action of reabsorption of sodium is again dependent on what? Aldosterone. And similarly, in the sweat glands, in our skin we have sweat glands and we sweat a lot when it is warm, okay, so far. And we lose a lot of there is a lot of in the primary sweat there is a lot of sodium ions, but it is again absorbed, okay, it is reabsorbed, and the sweat that we secrete is minimum sodium ions. But remember something, if there is too much sweat formation and if you lose a lot of sweat in a very short period of time, there is possibility that you are losing a lot of sodium. Okay. Therefore, it is a good idea to replace it with some salt rich drink. So what is the point I am telling you, that this is a sweat gland and it is also on the duct of the sweat gland you have what? You have receptors for aldosterone and they play the same role of reabsorption of the sodium ions. Okay. We have done this, so I can go very rapidly on this. The sodium. So let us imagine that there is loss of blood, okay, loss of volume, okay. What will happen? The done it, okay. Renin, okay. Renin will be released by juxtaglomerular cells, okay. Angiotensinogen, okay. Angiotensin 1, okay. Angiotensin 2, okay. And then that angiotensin has many effects. Some of them are directly on the smooth muscles. So, that angiotensin means what? Constrict the blood vessels and reduce the volume available for the blood, number 1. And number 2, stimulate aldosterone. Angiotensin 2 stimulates aldosterone, and then that aldosterone will absorb sodium. When you absorb sodium, it retains water, and when it retains water, okay, you are trying to compensate the loss of blood or loss of volume of the biological fluids. Is it very clear? So, this we have already done. This is just to tell you the juxtaglomerular cells, angiotensinogen, angiotensin 1, 2, 3, and then you will have the. So in the answer my question. What have we done? Well, go to the adrenal of rat, go to the zona glomerulosa, take one cell and map it here, single cell. Yes. And then ask yourself a question, in the plasma membrane, am I going to find a receptor for a peptide hormone? What is the peptide hormone? Angiotensin 2, okay. And do I find it there? We find there, okay. Can you see there A2 there? What does it represent? That is the angiotensin 2 receptor. Does it, what kind of receptor is having affinity for angiotensin 2? 7 transmembrane, same G protein coupled system. This is what? This is G protein coupled system, okay, and then it gives rise to, and then downstream you have lot of calcium. What do you have? You have lot of calcium, okay. And as a result of that, what are we doing right now? We are trying to study the response of a single cell of the zona glomerulosa, and it is responding to the arrival of angiotensin 2. And what is going to be the end product? The cell is going to release aldosterone. Very simple cell zona glomerulosa. Okay, we know that these cells are there to release the product, endocrine product, and that product is aldosterone. And we are seeing here a very interesting step. Okay, as a result of the rise in the calcium and these enzymes, etc., there is a, listen to this, a protein, and that protein sits just outside the mitochondria, sits on the mitochondria, outer layer, sits on the mitochondria, and that protein is called as STAR, STAR, it is called as, please somebody you can read for me, steroid what? Acute regulatory protein. Where is the protein sitting? On the mitochondria. Okay. What is the function of the protein? It is very interesting. If the protein is not there, the cholesterol molecule will not enter into the mitochondria. Got the message? Very clear message. star protein is necessary for, and it's a rate limiting, it is very critical. So as a result of that, you have the cholesterol, because of the star proteins, cholesterol molecule is now inside the mitochondria. In the mitochondria, it comes in contact with yet another enzyme which is called as P450. Now read this carefully. P450 SCC. SCC. Can somebody guess what is the meaning of SCC? Side chain cleavage. Very good. What is it? It's a cytochrome. The enzyme is called as cytochrome 450 side chain cleavage. As a result of that, the cholesterol is converted into what? Pregnenolone. We have already seen that. And then but this happens outside the mitochondria, then it is converted into progesterone, then it is, so is progesterone there in the adrenal? Yes. Is it a female hormone? Yes. Is this progesterone molecule being secreted by the adrenal cortex? No, no. It's just, so progesterone here is an intermediary molecule that comes into play, pregnenolone progesterone, and then it again enters, and then it is progesterone is converted to 11-deoxy what? Deoxycorticosterone converted to aldosterone. So this biochemical step happens in the mitochondria, it comes out, and then it is finally released into the circulation. Have we got the message now? So what have we learned just now? What have we learned? The regulation of the secretion of aldosterone under the influence of angiotensin 2, which is the most important factor that regulates the, okay.